Hi, Todd Dunn here on February 26, 2018, and this is video number 100 for me on YouTube. This video is nothing special despite being my 100th video. What it is though is a little bit of the science that differentiates MPPT solar charge controllers from PWM solar charge controllers. So what I'm going to be doing in this video is looking at a couple of graphs of solar panel output and explaining the significance of the data presented in the graphs for MPPT and PWM solar charge controllers. Okay, let's get going and have a look at the first graph. Oh, by the way, there are only two graphs, so it's not going to be that bad.
Okay, here's the first graph that I wanted to have a look at. And this graph is for a 100-watt solar panel. And what it is solar panel output versus panel voltage. And there are 5 curves here, and these are curves for different sunlight intensities on the panel. The bottom curve is for 200 watts per square meter. Top curve is for 1,000, which is the standard rating voltage for solar panels. However, we can think of these curves as proxies for a couple of other. The lower brown and green curves might be what you'd expect early in the morning from your solar panel or late in the day just before sunset, when there's not much sun intensity because the sun is either just rising or is setting. And the blue and red curves are what you expect around solar noon, when the sun reaches its maximum height in the sky and you get the most intensity on your panels. So these 5 curves can be thought of as a proxy for time of day. They can also be thought of as a proxy for the weather. On a bright, full sun day without a cloud in the sky, you might find yourself at noon looking at solar panel output somewhere on the red line. But on a completely overcast day with dense gray clouds, you might find yourself looking at a panel output like the brown line at the bottom. So these curves proxy for time of day and for weather conditions. There's also some additional information on here. You'll see the little, if we look at the red curve, right at the top of the red curve, there's a box that says MPP and an arrow pointing to a spot on the curve. That is what's called the maximum power point. That is the point on the output for this solar panel where it will put out its maximum possible power for this intensity of sunlight. And this MPP, not surprisingly, is where maximum power point tracking solar charge controllers like to operate. So if you had an MPPT charge controller connected up to this 100-watt solar panel in full bright sun at solar noon, you might expect to get 100 watts out of the panel. But what about a PWM controller? PWM controllers pass amperage directly from the solar panel to the battery without changing it. However, they operate at a voltage lower than the panel voltage, and in fact, they tend to pull the panel voltage down to the battery voltage or the charging voltage. The gray box labeled PWM is the voltage range at which PWM charge controllers work for 12-volt batteries. So that box runs from about 13 volts up to 14.5 volts, which is, as I said, the typical charging range. So where each curve intersects the gray box is the power that you can expect to get from a PWM controller, simply because we've pulled the panel down to that voltage range. So what I've done here is I've taken the power that I would expect to get out of a PWM charge controller for each curve, simply by reading the power off at 13 volts and at 14.5 volts, and then dividing that by the power that I would expect to get from an MPPT controller for the same curve. So for the red curve, maximum sunlight, I would expect to get 100 watts from my MPPT controller, and the PWM controller, if it was operating at 13 volts, say it had just started charging, would give me about 74 watts, and up at 14.5 when it was up into the constant voltage or absorption mode, would be giving me about 81 watts. And I've divided that power by the MPPT power to get a percentage of power for PWM versus MPPT for each curve. And you can see some interesting things here over on the right-hand side of the diagram outside the box. For bright sunlight right around noon, a PWM controller is going to deliver somewhere between 74 and 81% of the charge that an MPPT controller does. As the sunlight intensity decreases, either we move away from solar noon in time, later in the day or earlier in the day, or it becomes overcast and we don't get as intense a sunlight, we're going to see some variations. And you can see that as we go from most intense sunlight to least intense sunlight, that the PWM controller does a little bit better. And in fact, in very low light, the PWM controller will put out somewhere between about 78 and 89% of the output that the MPPT controller will for the same conditions. So there are a couple of conclusions we can draw from this. If you have a PWM controller, it's going to be at least 10% worse than an MPPT controller, independent of conditions, and potentially as much as 25% worse, simply based on the intensity of sunlight and the way solar panels work. So basically, this illustrates what sort of behavior you can expect, and that PWM controller is always going to be worse than an MPPT controller as a function of sunlight intensity, which is, as I said, a proxy for weather and time of day. Now, let's move on to my second graph. This graph is a plot of solar panel output in amps versus panel voltage. What it is three different curves for three different solar panel temperatures. The red curve is for 77 degrees Fahrenheit or 25 degrees Celsius. The blue curve is for 120 degrees Fahrenheit or 50 degrees Celsius. And the purple curve is for 167 degrees Fahrenheit or 75 degrees Celsius. And what this illustrates is that as the temperature of the panel goes up, the voltage of the panel goes down. And the point where the amperage starts to drop off as a function of voltage occurs at lower and lower voltage. I've also shown on this diagram where the maximum power point for each of these temperatures is located. And I've shown the voltage operating range for PWM controllers. So I used the same methodology as I did in the previous slide to calculate effectively the efficiency of a PWM controller relative to an MPPT controller output for panels at each of the three temperatures. At 25 degrees Celsius or 77 degrees Fahrenheit, the PWM controller gives 74 to 81% of the output of the MPPT controller. As we move up in temperature to 122 degrees Fahrenheit or 50 degrees Celsius, the PWM controller does a little bit better. And in fact, it ranges from about 88 to 97% of the output of the MPPT controller. And if the panel gets really hot, 167 degrees Fahrenheit or 75 degrees Celsius, the PWM controller's output ranges from 100% of the MPPT controller down to 92% when we get up nearer 14.5 volts. There's one other thing to consider, and that is that the maximum power point of the highest temperature curve, the 167 degree Fahrenheit or 75 degrees Celsius curve in purple, is right at 13 volts. So if your MPPT controller is operating at 13 volts, then basically it's going to just be barely charging your batteries, and it's never going to be able to pull them up above 13 volts. So what this points out is not only is a PWM controller not very different from an MPPT controller for hot solar panels, but the MPPT controller, when the panels get really hot, essentially won't work unless the algorithm allows it to operate at a higher voltage than the maximum power point so that it can actually put out some power. But in that case, the power output will be substantially less than it would be with a PWM controller. So this illustrates that as the panel temperature goes up, that the difference between output from an MPPT controller connected to a panel and a PWM controller connected to the same panel gets smaller. And in fact, at very high temperatures, the two converge, and also at those very high temperatures, the MPPT controller, if it has a straight maximum power point operation algorithm, will actually quit working.
All right, let's sum up what these two graphs have told us. First, the intensity of sunlight does have an effect on the efficiency of a PWM controller relative to an MPPT controller. Basically, in lower light situations, a PWM controller operates at a higher efficiency relative to an MPPT controller than it does in high intensity sunlight situations. The difference is in the neighborhood of 10% of efficiency. So in low sunlight, you might find that a PWM controller is in the neighborhood of 85% efficient, but in full sunlight, it might only be about 75% as efficient as an MPPT controller. So you're still going to have losses independent of intensity of sunlight, but the PWM controller will do better in low light situations, which would mean on overcast days and also early in the morning or late at night. Temperature, on the other hand, has a quite large effect, such that at very high temperatures, up around 170 degrees Fahrenheit or 75 degrees Celsius, remember these are panel temperatures, not air temperatures, the panel voltage output is going to drop to the point that an MPPT controller, which is tracking the maximum power point, might not work at all because the maximum power point will be lower than battery voltage. In that case, a PWM controller would still work and put out a reasonable output. However, at more reasonable temperatures, in the 80 degree Fahrenheit range, the PWM controller still has at least a 20% deficit in bright sun relative to an MPPT controller. The main consideration, realistically, is how you mount your solar panels. You need to mount them in a way that lets them stay cool. This is where rigid solar panels have an advantage over flexible or thin film panels. A rigid solar panel can be mounted with an air gap under it, which will keep the panel relatively cool. However, in contrast, flexible and thin film panels tend to be mounted directly to a substrate, like an RV roof or a boat's cabin top. This does not let the panel dissipate heat into the surrounding air underneath the panel because there is none. So the panel will operate at a much higher temperature than a rigid panel mounted with an air gap. So if you have your panels mounted directly to the RV roof or boat cabin top, and you live in a hot area, you might expect those panels to get pretty hot, and the result might be that you wouldn't really lose too much from having a PWM controller instead of an MPPT controller. The solution to that, of course, is to simply use rigid solar panels, which, although they're a little heavier, are easy to mount with an air gap so that they will stay cool. So basically, these two graphs illustrate why, except in extreme temperature conditions, an MPPT charge controller is always better than a PWM charge controller. Alright, if you found this video to be of interest and you learned something from it, give me a thumbs up. And please subscribe to my channel. So thanks a lot for watching.